Hello, everyone. I have 12 o'clock, so we are going to get started. Welcome to a dual webinar today for our Lunch and Learn webinar series. For our UF IFAS faculty, this is In-Service Training, Introduction to Water Resources Management in Florida. And this webinar is also part of the Virtual Water Ambassadors Program. The Water Ambassador Program is a stormwater education program held in partnership with Martin County and the University of Florida IFAS Extension. This is our last webinar for the in-service training and our penultimate webinar for the Virtual Water Ambassador Program. So thanks for joining us. I'm sure you're all pros by now, but just as a reminder, we have muted everyone's microphone. And if you are having trouble with the audio, just click that up arrow or that caret button next to the microphone icon and you can adjust your audio settings there. You have the ability to start your video, but we suggest you don't for bandwidth. You have a clearer picture usually if you don't. You can see the list of participants down there under the participant icon, and we will be using the chat box for all of our questions. We ask that you type your questions throughout the presentation, but we will hold them and discuss them at the end of the presentation. If you need to leave us for any reason, you can click that Leave Meeting on the bottom right-hand corner. And for the best viewing settings, we suggest you use the side-by-side mode, which allows you to see both the presentation and the presenter. We will be recording this webinar for those of you who have been participating in the in-service training. They're up at the IFAS BMP webinar page. Just go to past webinars and following the link there. For those of you who are part of the Water Ambassador Program, these and all of our previous Water Ambassador webinars are hosted on the Martin County Sea Grant Extension website. Just a reminder to please use the chat feature to ask all of your questions. And with that, I'm really pleased to present our speaker for today. Dr. Haimanote Bayabil is an assistant professor of water resources with the University of Florida IFAS. He's in the Department of Agricultural and Biological Engineering, and he's based down in Homestead at the Tropical Research and Education Center. And today, Dr. Bayabil is going to be talking about hydrology, giving us an introduction to hydrology and the DBHYDRO water quality data set. So with that, I am going to turn it over to Haimanote, and thank you all for joining us.
Thank you, Lisa. Let me share my screen. All right, can you hear me?
Yes, we can.
Okay, good. Thank you, Lisa, again for the introduction and for inviting me to present today. I will discuss two topics. First part of my presentation will cover basic introductory concepts about hydrology, including the hydrologic cycle and the major components of the hydrologic cycle, including evapotranspiration and runoff processes. The second half of my talk will cover the DBHYDRO environmental data set, what kind of data is available, and also how to access and process data from the website. So hydrology is a field, hydro means water, and it's about studying water. It deals with understanding and investigating how water flows on a landscape, both on the surface of the earth and below the surface of the earth. And also hydrology deals in understanding how water interacts with soil and other forms of minerals. And it deals with quantifying how water occurs, its spatial and temporal distribution, both in space and time. In general, there are two areas of specialization in hydrology, namely surface hydrology, which deals, as the name implies, about surface water resources, Groundwater hydrology is another area of specialization that deals about groundwater. But depending on the location, for example, like in South Florida, it's really difficult to distinguish and deal these two fields of areas, surface and groundwater hydrology, one from the other because of the nature of the soil and the landscape. These two continuously um, communicate or interact, and what we do on our surface water resources will have a direct and quicker impact on the groundwater. And in fact, the South Florida Water Management District has a combined management and decision support program. So the first thing that usually comes to mind when we talk about hydrology is the hydrologic cycle, something you might have learned from elementary school. We also call it the water cycle. I think the hydrologic cycle is one of the most important processes that exist and ensures the continuation of life, and also allows us to reuse water again and again and again. Without the hydrologic cycle, we would have run into big trouble already because water resources, specifically freshwater resources, are very limited. And without the hydrologic cycle, we would run into a shortage of water already than we see currently. It has a few major components. Starts with the precipitation, where we get rainfall from the atmosphere, and that rainfall, when it gets to the Earth's surface, will partition into different components. Some of it will be intercepted by plant canopy before it hits the ground. Once it hits the ground, it infiltrates, depending on the nature of the soil and the storage capacity of the soil and other factors. Some of that precipitation will infiltrate, and some will be retained within the soil root zone and eventually used by plants. Some will reach eventually to the groundwater, recharging the groundwater. Some fraction of the precipitation will be lost in the form of runoff and reach to water bodies, including the ocean, lakes, and water bodies. But that would recycle back to the atmosphere through the process called evapotranspiration, which is a combined process that involves the evaporation from lakes and any wet surfaces and transpiration through plants. If it was not for the evapotranspiration process, that feeds the atmosphere and ensures the continuation of the hydraulic cycle, we would, once we lose water for different reasons, like through contamination or water that gets into the ocean and becomes more salty, will not be available for use. So the beauty of evapotranspiration is that regardless of the quality of the water, if that water is converted to vapor through the evapotranspiration process, it will leave any contaminants, including nutrients or heavy metals or any contaminants behind, and only the pure vapor, water vapor, will be lost through the atmosphere, making the rain that would come back pretty much with a good quality. So evapotranspiration is a complex process, and that's the main machine that keeps feeding the atmosphere and ensures the continuation of the hydrologic cycle. As I said before, it involves two independent but coexisting processes. The first and the major one is evaporation, which does not involve any plants, any water, any wet surface, including plant leaves or surfaces, and oceans and water bodies evaporate, which means the conversion of liquid water to vapor. And evaporation accounts about 80% of the total evapotranspiration process. Transpiration accounts 20%. And if we talk about transpiration, it means plants are involved. Transpiration will not occur without the existence of plants. Plants transpire when they open their stomata to access carbon dioxide, and through that process, they lose water vapor to the atmosphere. This process is a very energy intensive process, which means it requires a lot of energy to convert the water molecules, liquid water molecules, to vapor, like you do if you heat water in your house, on the stove, or any using any heat supply, heat source. The water will start to evaporate and eventually leave the container and go to the atmosphere. And the same is true under field condition, but under field condition, our energy source is the sun. When the sunlight gets and hits the surface, including plants and oceans, any earth surface, and if there is any moisture on that surface, it will either be lost through evaporation, or if plants are involved, it will be lost in the form of transpiration. So studies have been done to quantify how much energy is required to convert a given amount of water from liquid to vapor. And evapotranspiration is one of the difficult processes, hydrological processes, which is really difficult to actually measure under field conditions. There are a few techniques, but it's very labor intensive, time consuming, and very difficult. And there are several indirect approaches of measuring evapotranspiration. And one of those approaches involve quantifying the energy requirements of water to be converted from liquid to vapor. So assume you have a field that covers about 1 meter square area with plants and soil, and expecting that there is unlimited supply of moisture, which means the plants are not stressed. And we expect evaporation and transpiration to coexist and take place. If you have a 1 millimeter thick sheet of water that covers that 1 meter square field, you would need about 2.45 megajoule of energy per meter square of area per day to convert that 1 millimeter thick sheet of water from liquid to vapor. And that's equivalent to 0.68 kilowatt hour per meter square. And imagine the surface area in the ocean, in the wetlands, and other water bodies, and the amount of evapotranspiration taking place every day, and the energy requirement to make that happen. The second major component of the hydrologic cycle is runoff, or overland flow. And there are two mechanisms through which overland flow or runoff occurs in a landscape. And this is understanding these mechanisms is very critical in hydrological studies and modeling and flash flood modeling and other purposes, including water management, decision making, and planning. The first is infiltration excess overland flow. That's a condition when you have a soil that's very less permeable or very poor in terms of permeability or infiltration, or when you have a storm event, a rainfall event that has a very low intensity, or a combination of these two. I'm sorry about the rainfall. When you have a rainfall that has a very high infiltration intensity, or a combination of these two. When the soil infiltration capacity is exceeded by the intensity of the rainfall, the soil will not be able to take in as much as water that's coming through in the form of rainfall. And at that point, runoff will occur, or overland flow will occur. Under this kind of scenarios, you might have a dry soil, which is still not completely filled by water molecules, and still see runoff in the field. The other process or mechanism through which runoff exists or occurs in a landscape is saturation excess runoff process. That's a process where you would see when you have a very conductive and highly permeable soils, sandy soils or soils with high gravel that we have in South Florida. or when we have a storm that has a very low intensity, or a combination of these two. What happens is that the soil has a capacity to absorb as almost all the water that's coming in the form of precipitation. But uh, if you have a restrictive layer at some depths, or if the groundwater is near to the surface, what happens is that all the pore spaces that are available in the soil will be filled up by water, and there will be no more room for water to go, and the only option is for water to stand on the surface and then start running off down the hill and eventually reaching to the ocean. The Soil Conservation Service has done a lot of research and came up with a simple equation that allow researchers to roughly estimate the amount of runoff from a given storm event. And their equation involves only two inputs: knowing the total precipitation amount in inch and the storage capacity of the soil in inch. And they suggest that the runoff amount from a given storm is the difference, the ratio between the precipitation minus 20% of the storage of the soil squared over precipitation minus 80% of the storage of the soil. But as I said, runoff is a complex process, and it takes many other factors affect the runoff initiation and the amount of runoff we can observe from a given storm event. And those includes not only the total amount of rainfall, but also the intensity, also how long the rainfall occurs in a given time span. Soil is obviously a factor in terms of storage, but infiltration is another factor. Depth is another factor. Land use, when you have developed land and non-developed land, you have different runoff response and runoff mechanism. And watershed characteristics or field characteristics: how big is your field, what's the slope, and so on. This is an example how the infiltration excess runoff, or when infiltration of the soil is exceeded by the rainfall intensity, occurs. Let's assume on the x-axis you have time from time 0 to time t, and on the y-axis you have rate of precipitation or rate of infiltration of the soil. So let's see that the blue bar plots are precipitation, and the black broken line is infiltration capacity. What this graph is showing us is that after the start of rainfall or precipitation, the soils would be pretty much dry, relatively dry, and they would absorb the rainfall at a higher capacity. But that capacity will significantly reduce as the rainfall continues. Depending on the soil, the rate of reduction in infiltration rate could be different, but generally the infiltration capacity will significantly reduce as the rainfall event progresses. And the point where, this point where the infiltration capacity of the soil is matched by the rainfall intensity, we will start observing overland flow. So anything, the green area and the orange area below the infiltration curve is the storage that has been taken up by the soil. Anything above this graph or the gray area is overland flow, something that is lost in the form of runoff and eventually lost to the oceans. Soil depth, as I said earlier, is another factor, or how deep your groundwater is also something that would affect how the way runoff is initiated. When you have a deeper soil, assuming it has a good infiltration capacity, it takes a lot of water before you observe runoff in the landscape. However, like we have in South Florida, where the groundwater is a couple of feet deep. The storage is very small, and that has a significant implication on the amount of runoff and the timing of runoff to occur after a given storm event. Another factor that affects runoff processes is land use, or the way we manage our land. Let's assume we have a watershed that drains to one outlet at the bottom here. And let's say that this is a hypothetical example. We have a given storm event, and the hydrograph, or the rate at which we observe the flow at the outlet, looks like this one. It's steadily increased, reached peak, and then came back to almost near to zero. Assume that we planted trees or other vegetation in the upper part of the watershed, and there is general understanding that trees intercept incoming precipitation, and also the biomass that accumulates below the trees in the root system enhances infiltration of water. This would eventually increase the overall amount of precipitation that has been retained or infiltrated in the landscape itself. And the effect at the outlet here, if we measure the flow at the outlet, will look like this one. The hydrograph will shift to the right, meaning the timing that you will see an increase in the flow at the outlet will be delayed because of the infiltration and interception effect of the vegetation, and also the rising limb, the rate at which the hydrograph increases is not as steep as it used to be, and the peak is smaller than it used to be. On the other hand, instead of plants, if we put parking lot or concretes, they don't infiltrate, they don't store any water, anything that falls on concrete will be runoff. And the effect of putting concretes or developing areas in a watershed would be something like this. We would observe runoff very quickly, right immediately, the storm event or rainfall event, and the increase in the flow at the outlet will be very steep, and it will be, the peak will be very, very high. That has, this has practical implications in flash flooding and other events. With this, I will shift gear and briefly introduce you the DBHYDRO environmental data set. And for full disclosure, I have started using this database, and I'm not an expert, and I hope that you would bear with me while I try to navigate the system. The DBHYDRO database is one of the most rich, well-maintained, and well-organized data sets related to water quantity and quality that I came across maybe in the world. I have looked at different data sets, and I never saw such beautiful data that's available for the general public for free. Anyone who has a computer and internet access can access this data, and it's a good thing to have. The data set is maintained by the South Florida Water Management District. They collect data from stations within the district and around the district. The total stations covered under this program are about 17,000 stations. Of course, the district collects data in collaboration with other agencies, including USDA, USGS, and the U.S. Army Corps of Engineers, and some state agencies are also involved in this data sharing program. The data they maintain and make available for the public are hydrologic data, climate data, hydrogeology data, and water quality data. Report or data availability can be requested in different shapes and forms. We can request raw data that has been passed quality control, quality check and quality control. You can do some summary statistics, min, max, and probability of exceedance. And you can request the data in the form of chart or download the data in CSV file, text file, or PDF files. Let me try to open the website. Okay. So this is the website that you would see if you search DBHYDRO environmental data set. It will take you to this website. This is their homepage that you'd see. And at the bottom, they have a video tutorial that will walk you through about the data availability and the steps that you would need to follow to download and access data. And I really suggest, if you are interested, to check their website and this video tutorial. I have watched this at least a couple of times. I'm not trying to reinvent what they have here, but show you what kind of data you can access and some of the interpretations and practical implications of the data. They have also a user's guide and a PDF file, a little bit long PDF file that with pictures that show you what kind of data and the steps that you can follow. And if you prefer, you can read their guide as well. If you click the main browser menu here, it will take you to another page where data sets are organized in different sections. The first includes hydrogeologic and physical data, including data from surface water, meteorological data, groundwater data, and water quality zones. You can search by data type or by station if you know the station, or by site name if you know the site name. They have also a very good interactive map here. They have other data sources that is available through the website, including evapotranspiration and rainfall data. Let me open their map. I like their map. It's very interactive and user-friendly. And when you open the map, the first thing that you'd see is this one. And as you can see, there is a lot of stations where the management district collects data and maintains data for. To know what's what, there is a legend here on the left side. All the blue color stations are about hydrometeorological stations, including wells, flow measurements, stage measurements, and rain measurements, and other weather parameters as well. Anything that's green is water quality related data. This is not the only data that's available on this website. If I activate the layer, if you see what is active now is only active monitoring stations that are already currently collecting data. But there are thousands of stations, maybe both for hydrometeorological monitoring stations and water quality monitoring stations that has been discontinued, but still data is available from. These stations, most of them were distributed throughout the management district, but there were a lot of water quality stations in the Everglades agricultural area that has been discontinued. South of Lake Okeechobee, I don't know why they stopped most of the stations, but if you are interested to look the water quality data, nutrient loading, and the others, you can check it out. Let me turn the inactive ones for now. So as I said, the beauty of this map is that you can visually look for stations for a given area of your interest. You can also type addresses like Homestead, Florida. So it's just like any Google map you can search, or if you know the the station name, you can search the station name. So let me take you to one of the stations in the near Biscayne Bay area. Some of the stations are on the ocean, some are inland. And one thing I forgot to explain is what this L, and if you see all the green states, they are labeled in different letters, L, O, G. L is logged. They have a data logger in a place, and they take continuous monitoring of water quality parameters. G is grab sampling, where people go out and take samples to the lab and do the analysis. I found the grab samples very, very detailed. When they do take samples, they do test the water for different parameters, including heavy metals and other emerging contaminants. The ones that are labeled L are mostly salinity, groundwater level, and sometimes pressure, barometric pressure. Okay, let me take you to one of the, let's see one of these stations. So if you click on one of the stations, tells you what the site name is, the station name, and what kind of data is collected, chemistry. There is a data logger there, and the start date, when that station started functional, and if it was ended, actually this one in July 21st this year. And if you are interested to see what kind of data is available from a station, if you click the DBHYDRO station information, it will take you to another page. On this page, it will provide you the lat-long coordinate system and the county and other additional information about that station. And if you are still interested to see the data, you click get time series data. And now it breaks down the data in different parameters. From this specific station, there is a well depth, barometric pressure, salinity, and conductivity. If you don't know what this means, if I check, for example, this, it says HBO, bottom pressure, temperature, degrees Celsius, water temperature. Sorry, I said pressure earlier, it's water temperature. If you are, let me open this, Sally, it's, the unit is PSU, and it's salinity. This one is specific conductivity. The unit is microsiemens per centimeter, and it's field conductivity. So the coverage is the same that we saw before. May 7, 2004 was the date it started. They started collecting data from this station, and it was ended on July 21st, 2020. But for some of the parameters, actually it ended earlier than that. Like, for example, a specific conductivity ended on January 5, 2005. They only collected 1 year worth of data. So let's check what we'd like to download or do some analysis. Like let's check depths and salinity here. If I check these two, I'm just choosing only these two parameters to get data for. Now it just kept only these two parameters that I wanted to look further, and the time period is from 2004, May 7, 2021. If I request all the data, it will, the system, the computer is slowing down, and I will request only a couple of years data. Let me make it 2005. 2005, 0101. Yeah, 2007, 12, 31st. If we request one value per row, and if you would like to see it on screen, I can request this, and the system yeah, it's working, I think. It looks like my computer is freezing, but it's working. Let me reduce this to 1 year data only. I'm gonna turn off my video if that would give me some bandwidth. Okay, we'll come back to this screen. Let me open another station.
I mean, we have a request if you could pick a station that may have saltwater intrusion as an example.
I thought salinity would give us some idea. Salt content is an idea, and I don't know a specific station that has a known saltwater intrusion issue, but if you know anybody could suggest, we can pick a station. But the reason I chose here, like salinity is salt, right? I thought, yeah, it's in the ocean, and the ocean is salty, but yeah, I really don't know a specific station that has that issue. Yeah, any idea, Lisa, or anybody in the audience who knows a specific station that, or area, maybe?
Yeah, any of the well fields. So the inland stations, the blue well fields that are sort of east of, yeah, where you are now, any of those well fields.
One of these, should we check out one of these? Let me see. Okay. So it's just depths. The wells, I found mostly they have only depths data. Okay, there is a chemistry here. Let's see what they have. What is it? Total chloride. Okay, we can check chlorine. Chlorine could be an indicator, right? 2000, let's say 16. 1601, 01. Let me request chart maybe. Oh, it is quicker. So the chart request, that's this is total chlorine. This is the well, the depths of the groundwater level in the well. Okay. So the well depths range from 1.5 to 5 foot, and the total chlorine from 30 to 60 milligram per liter. So when the well is deeper or drier, the chlorine level is also decreasing. The well went deeper, chlorine. So here, the well is coming from toward the surface, near the surface, relatively what's in here, right? and then the chlorine is slightly increasing. But the question is, why is the well increasing or becoming near to the surface? Is there a storm event? Is that saltwater intrusion? That's something we cannot tell from this figure by itself. If we had, for example, precipitation from the station and plotted, and if there is no precipitation at all, there is no reason that this well will come to the surface, and we could assume that saltwater intrusion is happening. But we don't have that precipitation data. But if there is a strong storm here, for example, and that would obviously drive the water level near to the surface, and obviously that should dilute the chlorine level in the water. But this seems something is going on. The water level is increasing, and for some reason, chlorine is also, concentration of chlorine is also increasing. And that water, it looks like it's not rainwater, because rainwater has a dilution effect. Okay, the data, if you request the data to look at it on the screen, it will look like this one. And if you can copy paste it, or even request the data to begin with as a CSV file and do the analysis on Excel. Let me open one rain gauge station. Okay, this rain gauge data. Very long, like 67, the earliest, and this is from this has data from 1997 to 2020, and then some of it is instantaneous, like event-based, and some is summarized total rainfall for a given day. And sometimes you see multiple data sets for daily total rainfall, but they have different data loggers or recorders. And for that reason, they provide the data in different in different options. So let me just check one of them, and let's say it's 2000 to 2009. This is a 9-year data, and if I click since this is rainfall, we would like to know the probability of accidents of a given storm event. So if I did the duration curve for rainfall events in that station, and this is the graph I got. What this graph means is that the rainfall, observed rainfall in that station range between 0 and about 2.5 inches. And the probability of accidents, or the chances that rainfall at that location will be more than 2.45 or so, is nearly like about 1 over 100 is 0.01. So the way you interpret this result is that there is only 1% chance that the rainfall will be 2.45 inches or more at that station. And if you are interested, then I'm like the storm year of this station is that if you divide 1 by the probability, which is 1%, which is 1 divided by 100, 1 over 0.01, that would give you a 100-year event. So if you have 2.5 inch rainfall, that means that's a 100-year storm event at that station. So this breaks down the number of occurrences during that 9-year period. Storms that have values between 0 and 1.75 or so were about the maximum 8. This is the range, and they were about between 1,125 or so storm events. The next is between 175, 1834 and 36. There were less than 50 events, and then most of the events were between these two values. And this is again the number of storm events, and then the maximum is 0, no rainy days, and the next is about 1.78 inch. There were about 175 storm days that recorded that amount of precipitation. Okay.
So we are at 1:45. I'm going to invite everyone to ask questions in the chat box while Haimanote continues to do the DBHYDRO.
Yeah, I mean, I am almost done, and I can stop actually. Yeah, I can stop, and I will take any question that you might have, and would be glad to answer. Thank you.
Thank you. Looks like you might be off the hook. There are no questions yet.
Not yet. So Lisa, do you know any list where like we can find wells that have saltwater intrusion, specific wells? I mean, that would be something I would be interested to identify wells.
Yeah, so Barb McAdam, who's based out of the Homestead office, she's with the Florida Friendly Landscaping Program. She said that they have a graph
Indeed?
from Water and Sewer Department, so you can connect with her or she can connect with you. I also believe USGS has some information about, as does the Water Management District.
Yeah, I was surprised because some of the wells that are inland have intrusion. In fact, I thought my expectation was mostly the ones near to the coast would be more vulnerable.